an analogy to help understand some of the bigger picture. Spectroscopy. So we have an atom, protons, neutrons in the center, electrons orbit around it. It's kind of like onion layers. You can picture onion layers, and each groove is a specific location of the electron, probabilistically. You can picture a dot going around. Now, if you take another dot, like a piece of light, a dot of light, a photon, and you throw it in there, and it hits at the exact energy. Each of these layers has a specific amount of energy. If that dot has a specific energy and it hits that electron, then it causes it to jump to the next layer, and it gets what's called excited. So, once it's excited, then it eventually wants to be closer to its, I think it's called a ground state. So, it'll drop back down, it'll spit that piece of light back out. It'll spit the piece of light back out, probably in a different direction than it came in. So by knowing that, if you have a light and you have some type of gas, say hydrogen or something like that, which don't try that at home because hydrogen's highly flammable. So anyway, light shines through the hydrogen gas. So the hydrogen has one proton and electron. You can have a neutron if it's an isotope called deuterium. But anyways, proton and electron. So piece of light zaps it. It gets thrown out a different direction. And it doesn't arrive at the sensor right in front of the light for the hydrogen. There may be other stuff in there too, like oxygen and nitrogen, whatever's in the air. But anyway, for that specific light pattern, if you zoom in like on the rainbow color looking thing, that specific light pattern, you can see little like black lines where the light didn't arrive, and those are specific frequencies, like if you know the rainbow colors, red, orange, yellow, green, blue, indigo, violet, that's from wider wavelength to skinnier wavelength. Wavelengths from the top of one wave to the top of the other. It's basically a full wave cycle. So you have smaller wavelength as you go from red to orange to yellow to green to blue to indigo to violet. So those are specific wavelengths, they're called. Distance from, just say, the top of one wave to the top of the other is the wavelength. Now you have a wavelength of a certain amount, and that's its specific energy, I guess you'd call it. So whenever you look at that spectrum of the visible light, if you zoom in really close, then you can see those gaps for specific energies. And those specific energies, if you see which ones they are, and if they match what was shown in a lab with just say hydrogen, then you know it's highly probable that it went through hydrogen gas. And you don't have to test it once you know the numbers for the hydrogen, like the specific wavelengths for the excitation of the ground state of the hydrogen. So that's how people figure out a lot of what the sun's made of. The light shines through. There's hydrogen and helium are the frequencies that don't show up. In other words, the black lines in there, the gaps. So that's because the photons hit the hydrogen and it slung them out in a different direction, so they didn't arrive at the target. They didn't arrive at the sensor. So that's kind of how it works for spectroscopy, and that can be used like for a lot of things, and it can be used to detect different types of gases on Earth, in the sky. That's another interesting thing to me about atoms. Anyway, that's some cool science stuff, and hope you enjoyed the video, and click like and subscribe, and let me know what you think. Bye. Thanks for watching.